Hello, my name is Ralf Walter. I'm working at Infineon Technologies, and there I'm responsible for the low voltage drives. Today we will cover a typical problem which occurs in an electric driven motor. That means a short time overload. This means a current overload for 1 second. Just to show you what is important, we will have a closer look today to our special part, the BSC 016, a Super SO8 with 1.6 milliohm. To understand what happens during that short time pulse, that in that case 1 second for 25 watts, we will open the case, and there we will find, of course, the lead frame, the chip, and the connection of the source, this copper clip, which is connected via 2 points to the chip. To get first hints, we can look to the data sheet. There we will find the SOA diagram. But it's easy to see that here the time constant of our part is very short. You see here the line for 10 milliseconds, and the next line is already continuous mode, DC. Another useful diagram for short time pulses is the ZDH junction case diagram. And here you see also that after latest 100 milliseconds, the chip itself is completely heated. It works in continuous mode. Compared to our 1 second pulse, this is not useful. Additional information you get if you use our PSpice library, which are available in the internet. You see here the thermal equivalent and simplified schematic with the thermal resistances, the thermal capacitance. The figures themselves you find also. Here are the typical values, and on the right side you will find the maximum values. Just to have a simplified look to that setup, let's summarize a little bit. So you will find an overall thermal resistance of 0.65 Kelvin per watt and a thermal capacitance of 0.068 watt seconds per Kelvin. But what does that mean for our problem, for our 1 second pulse? Let's calculate the thermal time constant. Here we see it's around 44 milliseconds, which fits perfect to our diagrams. Okay, 45 milliseconds is much shorter than our 1 second pulse. That means we need additional calculation hints. So now we have a closer look to the complete setup, a typical setup, a Super SO8 soldered to an IMS board. That means it's an insulated metal substrate board with a really thin thermal insulation material and an aluminum carrier which can act as a thermal tank, a thermal capacitance. Okay, to calculate a little bit the thermal behavior, we use our pocket calculator and first calculate the thermal resistance of that really thin interface material. The thermal resistance is around 4 Kelvin per watt in that case. Okay, using well-known parameters, we can calculate the thermal capacitance of the aluminum material, which results in around 0.4 watt seconds per Kelvin. Does that help? Let's see. If we now summarize all thermal resistances and thermal capacitances, we get around 4 Kelvin per watt, a little bit more for the thermal resistance, and a little bit less than 0.5 watt seconds per Kelvin for the thermal capacitance. First, calculate the temperature rise looking to the thermal capacitance. Here we have our 25 watt power pulse. Time duration is 1 second. This results in a temperature rise of a little bit more than 50 Kelvin, 50 degrees Celsius, which sounds very good. But if we take the complete setup, we will get a time constant of more than 2 seconds, which is compared to our 1 second problem, the 1 second pulse, too big. So that means the reality is somewhere between the first time constant, 44 milliseconds, and the second one, 2 seconds.